Right, and I believe the recording has started. So I guess we should just introduce everyone. So welcome to session number 2 of Building Success. Today's session is focused on building and is titled Parts, Mechanical Systems, and Applications. So we'll begin today's session by just acknowledging that the Wurundjeri people of the Kulin Nation are the traditional owners of the land on which today's workshop is running, and that we would like to pay our respects to their elders past and present, and we'd like to extend that respect to all of the Aboriginal and Torres Strait Islander people who may be here today. Moving on, who are we? So I'm running this workshop again, along with my old teammate, Anthony. Me and
Hello.
Anthony both have the same achievements because we've been doing Vex together for the exact same amount of time. We've been on the same team the entire time. So yeah, both of us, we are the 2-time Australian National Champions and Excellence Award winners. We have both qualified for Worlds twice, and we have won 3 state champions and Excellence Awards. So that is both within Victoria and also over in the Australian Capital Territory. And as an additional kind of achievement, there's only one thing Anthony's achieved, which I haven't. One thing Anthony's achieved that I haven't. He is the only person to drive a robot off of a table at Worlds.
That's the most pristine achievement.
You were there for that one, so
yes. I happened to be walking past and watched Anthony drive it off, and it was very comedic.
I wasn't so happy about that one. I remember.
But
you guys told me.
It proves our reliability with our robots, because afterwards you can't deny it. It
still worked. It actually worked better.
Exactly. Our accuracy went up.
Anyway, and then we have a special guest today, a surprise guest, and we've got Jacob. So did you want to introduce yourself?
Yeah, hello. I'm Jacob. I'm the current head referee for New Zealand, and I'm also the leader of the New Zealand Auckland University Robotics Association's Vex team. Not the club itself, but the Vex team in it. So Aura, you may know them by. I'm 2020 New Zealand National, 2019 New Zealand, no, that's 2020. My brain's on a mess right now. 2020 New Zealand National Excellence Award winner, and I'm 2019 Worlds Division finalist, 2019 Vex Virtual Worlds Programming Challenge winner. That's one of the online challenges that they used to offer. It got discontinued in 2020 with the change to V5, as that was done in Robot C, which is kind of discontinued now. And I got the 2019 World Service Award. So I came away from 2019 Worlds with 3 trophies. I've qualified for Worlds 3 times. One of them didn't really happen, as it was 2020. It was online COVID, but I've been to Worlds twice before that. Once in Starstruck in 2017 and in 2019 for Turning Point.
Cool. Okay. So yes, as we said last time, this is who we are, and this is why you should trust our opinion, because we have a lot of experience with the 3 of us, and hopefully we can kind of share some of that with you guys today. So for parts, mechanical systems, and applications, we're going to kind of talk about, you know, the Vex system and Clawbots and how we use the Kaizen model. More specifically, it's a model myself and Anthony use, which is all about continual improvement and getting from robots that look like this, that aren't particularly great, into more advanced robots that you would see at Worlds and that you would see at the world stage in the Dome. So I guess we just want to start off with let's go on, the Vex website, right? There's the Vex store, and there's a lot of different parts available on the store. There's a huge range, a lot of equipment you can buy. So what we've done is, over the next few slides, we've kind of just condensed some of the parts that we think are the most important from the website and that you will see the most, and also maybe a few little unique applications we can use, a small discussion on each of these part categories to go over what they can be used for. And then later on, we're going to talk about kind of how these are all used together to make mechanical systems, like different drivetrains, different shooting mechanisms, intakes, and various other things that you will use in the competition. But before we do that, it completely slipped my mind. We have to just quickly take attendance. So what I'm going to do is I'm going to send an attendance form whilst we start this. And just everyone that is a part of the Melbourne University Vex Robotics Club. So if you're a coach or you're from another school, you don't need to worry about filling it out. But yeah, if you're from our team and from Melbourne University, we need you guys just to fill out this quick little attendance form, and I'll chuck that in the chat.
Spencer, real quick, do you think we can invite other people from the Vex Australia server?
Yes, I've already posted in there. So if anyone wants to join,
they do say they don't have access, unfortunately.
send a link. Sorry.
Mm-hmm.
Oh wait, no, that's the wrong link. Hold up. Sorry, guys. Just take a little quick 20-second intermission here to fix this up. Might have sent the wrong link before. Okay, if you want to tag them with that. Cool. Okay, anyway, sorry, back to the presentation. If you guys can just do that attendance form, we'd really appreciate that. Okay, so the store. So first kind of section of parts we're going to go over are the wheels. So Vex offer a huge range of wheels, and they're all offered in different sizes, typically 4-inch, 3.25, and 2.5-inch wheels. And I guess I'll just kind of hand it off to Jacob and Anthony to kind of talk about how all these wheels might be used.
I will take the Omni wheels first. Well, generally, every team should be using Omni wheels purely because of just the low coefficiency for friction. When
just a clarification for anyone that doesn't know, Omni wheels are the top left one.
Yes, the one with the miniature rollers, if you can see them. The main reason why people generally wouldn't use this more is purely because because they roll side to side, they allow for very sharp turns compared to a normal traction wheel to your top right. Would that be? Yeah.
Yeah. Think about how a tank can run both sides of its drive sideways and turn around, but your car cannot turn on the spot as well. Well, it can't at all.
Yeah.
It's sort of like you're reducing the friction sideways because the wheels have to drag sideways as you turn on the spot. So the rollers can roll and it can turn better.
Think about it as like a robot can just rotate on its center axis instead of a robot that can just turn at a 90-degree angle from its base, from its rear to its front.
Yeah. So just, yeah, you guys have already gone over that. What do you guys think about traction wheels in general? What would you use traction wheels for more?
Jacob, you can go for this one.
So for traction wheels, the main use you'd see in Vex is placing them in the center of your robot when you've got a 6-wheel drive. They don't have these rollers, but if they're at the center of your robot, they're not dragging sideways as you turn. And so what they then allow or prevent is, because they don't allow sideways movement, you won't get pushed along as much when people drive into the side of your robot. The issue with traction wheels, however, is despite their name being traction wheels, they have less traction on the Vex fields than the Vex Omni wheels, unfortunately.
Which is kind of like an oxymoron.
Yeah.
And for you to achieve better traction than the traction wheel itself is if you just like slide just any material in between the rollers on the Omni wheels, it'll just stop it from moving, and you can use them as a normal traction wheel.
Which would be a locked Omni wheel, which we've seen used competitively a lot. Yeah. Just kind of want to quickly skip through this about mechanism wheels, maybe what we see those used for more. So mechanism wheels are the bottom left wheel here.
Mechanism wheels, what they allow you to do is the rollers are angled 45 degrees. And what that means is if you independently control your all 4 wheels, you can call or make the drive go in any direction through the amount of power. Running the front wheels in the opposite direction to the back wheels will allow you to drive left and right. running them at the same way will allow it to drive normally, and a combination of whatever can allow you to go on diagonal movement.
Just to clarify, when he means left to right, he means you can just keep the robot centered, and you can just strafe
So
from
you can
left to
strafe
right
left to right. Yep.
Yeah.
without having to turn the robot.
And then last, we have the wheel legs, which we don't see used very often, at least at a more competitive level. But what is kind of an example application that they might be used for?
If
That's a good question there, bud.
If you are to come up to some sort of problem that involves climbing up stairs or something, they will have a better ability to climb stairs as they step up on it rather than trying to get the traction on the side of the stairs to lift you up onto the step. So they are useful for small climbs on stair-like objects. So there were a few teams that liked to use them in one of the season's turning point that had platforms that you would be climbing up. They ended up not being that effective at it because all the other wheels could do it just fine. But it is an option.
Basically, what those wheels are usually meant for, they're just good for demonstrations at like conventions rather than for competitive use. That's why you rarely ever see this in general in day-to-day competitions.
Yeah. And then there's also the whole idea that there's wheels available in different sizes, as we mentioned before, the 4-inch, 3.25, and the 2.5. And you were kind of explaining this to me yesterday, Jacob. I don't know if you want to mention it, but generally that the wheels are narrow and smaller, and then that causes them to have, did you want to explain that?
The 3.25-inch wheels, they have a narrower width. So they're easier to fit into a narrow chassis. If you want to make your drive width quite small, then the 3.25s are good for that. And on the foam field tiles, they have a firmer plastic than the 4-inch Omni wheels, which allows them to grip better because they sink into the tiles better, and you've got that better pushing force. However, this season in particular, 4-inch wheels are being used more than previous seasons by competitive teams because with the whole softer rubber, it compresses down and gets a better coefficient of friction on the platforms. It climbs better. The 3.25-inch Omnis have been spinning out. An additional point to this is the traction wheels. They are slightly smaller diameter than the Omni wheels. So if you were to have tractions in the middle of your robot for the not getting pushed sideways aspect, they don't actually come into contact with the platform as you're climbing it, because the 4-inch Omnis are 4.125 inches, not 4 inches. And the 3-inch Omnis are 3.25 inch.
All right, that's right. And just kind of a really unique application that the Omni wheels can be used for, which a lot of more professional teams might not know about, just a kind of little tip that we'd say is that they can actually be used as an anti-tip. So this is an example of our friends 240p and what they've done. So this is on their robot called Low Quality during the turning point season. So what they did was on their double reverse 4-bar, which we'll talk about later, they decided to attach Omni wheels so that because it's kind of very top heavy, that sometimes the robot would tip over and fall backwards. And that when falling backwards, it would land on these wheels so that even though the robot had fallen and might not be able to kind of use its lift, it could still drive and it could still act as a push bot. So if you can kind of imagine that's tipped over, the front 2 wheels are at the top still spinning, but then it's using the rollers from those wheels, so it's still able to drive around. That's a cool little tip. I don't know if anyone kind of has gained anything out of that, but it'd be amazing to see that at competition. And it's kind of just a useful little competitive application. Okay.
An alternative to that is designing your robot to not tip over.
That would also
just get good, really.
And then we've got linear slides here. So linear slides, these are used for various different things. Did you guys want to go over what you might use linear slides for?
Generally, many teams wouldn't use this, rather opting just to make their own. But the main purposes for this, predominantly in one season of Vex Robotics, was in Turning Point, where they used these components just to make a puncher, and that's just really what it was.
And that's something we'll go into more depth with a bit later.
So the reason that a lot of teams don't use the Vex linear slides is they just have quite a high friction in them. The old ones were steel on steel, and the new ones is plastic on steel, but it's just not designed the best. When you make your own custom ones, you'd probably use rollers to reduce friction, whereas this is just straight sliding on sliding action.
Yeah. Okay. Moving on. Next little kind of part we have are bearings and flat bearings. And they're just kind of used to reduce friction at specific points that require a lot of movement. So kind of where you attach your axles and shafts in. Is anything else to add, or is that kind of just a small little?
I think a little tidbit that we can use. The pillow bearing, if you guys don't know what a pillow bearing is like in the top left corner, top leftmost corner. The main reason people would use these type of bearings are purely for if you want to change a hole position from vertical to horizontal or horizontal to vertical. And they could also use as attachment points for, say, bracing or anything else in between that, really. But aside from that, they are not really used all that often.
Generally, you should definitely use this. If you're attaching, you got a C channel and you're putting a shaft through, make sure you're using a bearing, because if you're not, there's going to be a lot of friction and it's kind of, Tank treads and sprockets, quick little jump into those.
Jacob?
Okay, so in Vex, we have two types of sprockets. We're not going to go over standard sprockets here, but they come in two sizes, sprockets and high strength sprockets. Standard sprockets have such small chain that it snaps way too easily. No one in a competitive environment considers it. So what you see here is high strength sprockets and high strength chain. You can interchange the chain with tank treads to make tank drives or conveyor belts or whatever. There's multiple types of tank treads. So if you look on the top left, you've got ones that you can slide padded mats in or flaps in that allow you to make flap style intakes and whatnot. Or you can use, there's green links that are often used for just between padded links, like the one, not the top left one, but the one below it, for tank drives. You don't see a lot of tank drives because the risk of them snapping is a big problem. Was there anything else I was supposed to go over here? When you're using sprockets, you should use the largest sprocket you can fit without sacrificing other parts of your design, because you want to keep the wrap angle around it as much as possible to reduce strain. So using the small 6-tooth sprockets at the bottom right there, you put a lot of strain on the chain if you try to power it via that, and it will likely snap. Whereas if you power it by a 24-tooth, which is is there a 24-tooth? I'm forgetting the sprocket amounts. Larger sprocket, then it won't snap as easily.
I believe this could be just my head canon, but the main reason why people, or you would generally never want to use the smaller sprockets, is because if it does wrap around these smaller tooths, you're not sharing enough load across the chains, so it just increases your chances of snapping. Whereas you use the larger sprockets, you're sharing the load between a larger amount of chain surface area, just so it decreases your chances of snapping it.
Yep.
Is that correct?
Yep.
Sort of, but you'll always have the snapping will be at the chain with the most pressure tension under it, which will be at the top, or they don't really have much tension on them when they're in the middle on the side of the sprocket.
All right, next thing, we've got just gears. So gears come in both low strength and high strength varieties. Typically the high strength ones are used much more. It's in the name that they got more strength. Did you guys want to just quickly go over gears?
Yeah. Generally, a good rule of thumb is to, if you can see if you notice there's a very thin gears, and on the left left side or right side, sorry, there's much more thicker gears. Basically, you would generally want to use these thicker gears on more strenuous portions of your robot, say the drive on the robot or any lifting mechanisms on your robot. You would generally want to use this more. And for the thinner gears, you would just want to use it for low friction purposes, say a flywheel or some, I don't know, other low strength applications would be what, intakes would be a good one. Yeah. Yeah.
Yeah.
Did you have anything to add, Jacob?
The low strength ones are fine in a lot of applications. The issues you see with them is Vex is very special and designs them with these lines cut into them that work as fracture stress concentrators. And so it's a lot easier to snap through those. You can snap teeth off in some situations, but I think with low strength gears, I've personally snapped the inside of the gear more than the teeth. I have snapped teeth off of high strength gears in very high stress situations, such as on a catapult that is having high impact repeatedly. But generally, as long as you ensure that you're not overloading the gears and you're not doing repeated impact loading, they should be fine. Drive is it reverses a lot. You'll be driving forward and then suddenly want to go backwards and you won't let it roll to a stop. You'll start driving backwards. And that is a high like hammer load on the gears, which is why low strength gears sometimes will not handle a drive as well, especially if you have more motors. Like that robot that I've snapped the most on had 8 of the old motors, which is probably close to the force of a 6-motor drive. They say theoretically that should be a 4-motor drive on V5, but I think the loading was more like a 6-motor drive running through those gears. So if you are to use them in a drive, it's probably best to have high strength on the wheels themselves, which is where the most load will be running through.
Yeah. And just to add kind of onto what these guys have said, another kind of cool application for the gears is that you don't necessarily just use them as gears. You can use them as gear ratios to kind of change the torque or the speed of different kind of outputs. So for instance, we had a gear ratio on our flywheel a couple of years ago, which would, did we increase the speed of the flywheel using the gear ratio, right, Anthony?
Yeah, it was a 1:5 and the input was a 600 RPM cartridge.
Yeah, so then there's also ways you can increase the torque. So like if you want to climb onto a platform, you can actually use the gear ratio to increase the amount of torque you have in the wheels rather than the speed. So there's a lot of ways you can use gears to change the output of motors and also to affect how motion works with the robot. So overall, they're really important. And yeah, gears
Generally,
very important.
Mechanical change in speed will, if your speed increases, your torque will decrease, and vice versa. They're inversely proportional. If you change it in software, decreasing the speed will decrease the torque as well. No, that's awkward. That's kind of motors don't follow a linear curve there, but you should try to get the desired speed and torque via gearing rather than relying on later software control to bring your speed down or up.
Yeah. Okay. Next kind of section, we just want to talk about standoffs. So they're kind of just used to separate different components without using bulky features. They're also kind of more aesthetic spacing. They provide a lot of structure, reinforcement. They allow for connections that are longer than the 2-inch screws. And they allow to extend connection points. Is there anything else?
And,
or is that...
I believe we could also use, we've used these standoffs a lot in a lot of ways that normal people wouldn't generally think of. In one application on our original, on our last robot in Turning Point, we use these as rails for a cascade tray, where the standoffs would just go into a hole and it would just like extend our tray by a couple inches. it would just allow us to intake more cubes. But yeah, other than that, these are just really reliable and versatile pieces of kit in any team.
Yep. Next up, we've got the Winch Pulley Kit, which is kind of not used that often by a lot of teams. I'd say, Jacob, have you ever used a Winch Pulley Kit?
I don't even think we have one.
Yeah.
We have custom winches every time we want a winch.
So
and pulley.
it's something that people don't really use, but I thought just some kind of like a unique little application that we should mention is that using these little pulleys, if you see on the top image, on the very right, little red circular objects, what we did, Anthony, was for our tower takeover robot, a lot of teams, when they do tensioning along their lifts, they often use like standoffs with a little spacer at the end. So they wrap it around and it's not really even. So what we were doing is we were using the pulleys as a way of holding our rubber bands for our tensioning. So it's not something that people would go, oh, I'm going to buy a winch and pulley kit. People don't usually use winches and pulleys. They might buy the kit to use the pulleys for tensioning, for instance, which is what we did.
And another application for these was that those pulleys were also good when using as rollers to use as like to roll against the surface of the walls, as using other methods would have been too bulky or just too small. So this was a very nice in-between method for just rolling against the surface.
So I'm pretty sure we had them on the corners of our robots that when it would bump in, it would kind of just
self-center.
Do you have anything to add, Jacob, or is that?
I was just going to say the other thing about that kit there that I'm seeing is there's a ratchet there.
Yep.
So if you look at the bottom left, there's a gear that has teeth that are rounded up on one side and flat on the other. And then there's this little tooth. What that allows is you can run it one direction. The gear will rotate one direction and it will keep tightening something. But if you run it the other way around, it will just click around. It won't. Oh, if you run it one way, it will click around and will be happy. The other way, it will provide force. So an example of that is when you're riding a bike, you can push the pedals one direction and the bike will move forward. But if you run them the other way, they just make some sort of clicking sound and don't do anything. That's sort of how a ratchet will perform. Yep,
beautiful. And then there's only a little bit more parts we're going to go over, and then we're going to go into more depth about what the kind of the systems we use with them for. So next up, we've got pneumatics, which teams kind of have overlooked the last few years with V5 because there used to be a restraint where you could only use your 8v5 motors and you couldn't use any pneumatics, but now they've changed it. Is it 6?
You could sacrifice 2 motors to have pneumatics.
Which pretty much every team was like, that is definitely not worth doing because the V5 motors are much better and you could use those to achieve what the pneumatics do. But now we have the 8 motors plus pneumatics, so that you don't have to sacrifice them anymore. So it's kind of like if you had an additional function that you wanted to do, but you didn't have enough motors for it, it's something that you could use the pneumatics to do. So one example of something we did was during Turning Point back, I think when we had V4, I think it was, we could afford to do it then. What we did was we had the pneumatics at the bottom of our robot. So we'd have the 2 cylinders so that when we'd go on the platform to park, we'd activate the pneumatics and they'd push down these little kind of paddings, which would lift the robot up a bit. And it had anti-slip mat. So it would make it, because we had Omni wheels, right? So at that point, and then when teams would try to push us off the platform, we'd kind of be stuck to it. So it's harder for teams to push us. We've got more traction on it. So there's little tiny applications like that you can use them for. What are some more?
If you don't know what pneumatics are, they're air-powered pistons. So just linear movement. You pump up a tank with a bike pump and can fire it however many times you want in a match till it runs out of air.
There's different pneumatic kits as well. There's single acting, there's double acting. So there's like kind of a huge range of different ones you can use, and it's really fun to play around with.
Some of the generalization of applications for the pneumatic kits were, what I've seen is that people use these as deployments for gates, and especially in tower takeover, where someone was scoring just one giant tower, and then they would just deploy gates to prevent people from trying to knock it over. And what was it? A few other applications where they also use this for a lift on a robot as well, where it doesn't require a large amount of motion. So they can use this as a quick, an easy way to lift up a mechanism just for that, really.
Yeah.
Okay.
Something Spencer mentioned before was there's single acting and double acting. So single acting are like what you see in the bottom left there. There's a red ring. That's where the air goes in, and it only goes in one end. And then that fires the piston. Then if you release the air pressure behind it, then a spring pulls the piston back in. With double acting, you don't have the spring, you have an air intake at both ends. So you will put pressure into one end and it'll fire out, put pressure into the other end and fire back in, which will allow you to have more force at pulling back in than just that spring. What my old team used to do is we didn't want to spend the money on single acting pistons since double acting pistons had more uses. And if you wanted to use a single acting piston, you just didn't put the air onto one end, you just left it open and you used rubber bands to return it instead of the spring.
Yeah. Okay, well, that's kind of just a summary of like some different parts we have. There's a lot of other parts that we didn't go over, like C channels. There's some other kits like turntable kits, the tank tread kits. We've decided that because they aren't as useful and stuff like C channels, it's like really generic. It's just for construction, that we can kind of leave that up to you guys to imagine what you could do with it. But these are kind of the parts we'd say are really important to use, and also just to kind of get you thinking about kind of different applications you might have for using these. And also so that when we now show you the systems we're going to get into, that you guys have an understanding of what these are. So we've got a couple of videos today. Only one of them is a bit of like an explanation video. And yeah, so we're starting off with our drive systems. So we're going to talk about drivetrains. And yeah, we have this quick, it's about, I think it's a 3-minute video. It just goes over all the different drive systems. I feel like it'll probably explain it better than we will. But then we're going to do our own little explanation afterwards and we're going into a bit more detail. So I hope you guys enjoy this video. So yeah.
Vex Robotics has a number of different wheel types, but what's the big deal with Omni wheels? What advantages do they give you? Welcome to Kepler Electronics. Vex sells a number of different types of Omni wheels, but I will be using the classic large flavor. Omni wheels have rollers all along the circumference, which allows them to not only roll like a normal wheel, but also move sideways, allowing you to do some cool things. The most common type of Omni wheel configuration is the tank drive. This configuration is your standard 4-wheel setup, which can move back and forth and also be pushed from the side. This can be a disadvantage, but it allows the wheels to pivot more effectively, putting less strain on the motors. This was a big deal back in the Cortex days, but with V5 motors it probably isn't that big of a deal. One thing that takes up another motor but could potentially be a worthwhile addition is a 5th wheel in the horizontal direction. This can help you strafe sideways, allowing you to line up shots and shoot with more precision. You may have to create some sort of system that keeps the wheel in contact with the ground, because this wheel sometimes worked but wasn't in contact with the ground as much as it should have been, which means that if there was a lot of weight on the robot it probably wouldn't work at all. This setup takes some effort but could potentially yield some neat advantages. One other tank drive configuration is the hybrid setup. This setup involves swapping one pair of Omni wheels for normal wheels, therefore getting the decreased strain on the motors because one set can slide effortlessly across the floor, and you are much more protected against pushing compared to the full Omni wheel setup. This setup has perhaps the best pro to con ratio, with the only main con being that you can't use a middle wheel to strafe, but that's a small price to pay for not being pushed around. For the next wheel type, we'll be moving on to Mecanum wheels, which simply look awesome. They feature angled rollers and come in 2 counter-rotational flavors. Mecanum wheels are used on industrial machines such as forklifts because they allow you to strafe sideways, keeping your front end pointed towards the target, which allows you to line yourself up with more precision than a standard tank drive. With Omni wheels, you want to set each pair at opposite corners so that your front 2 wheels are either pointing towards or away from each other, and the opposite for the back wheels. Let's call these 2 wheels the A wheels and these 2 wheels the B wheels. When you turn the A wheels forward and the B wheels in reverse, you strafe to the right. When you turn the A wheels in reverse and the B wheels forward, you strafe to the left. You can still drive forward and backward like a normal tank drive, along with turning in place. But disadvantages? Not a lot. From what I could find, the main disadvantages are that they have less traction because they're giving up surface area for the rollers. Mecanum wheels also typically weigh more than traditional or Omni wheels due to the increased width. Mecanum wheels are pretty cool and fun, they just require a couple of minor trade-offs. Finally, we come to the lord of all Omni wheel setups, the holonomic drive, commonly referred to as the X drive. This setup features 4 Omni wheels arranged at right angles to each other. The example shown here is nowhere close to the size restrictions of VRC and isn't a particularly secure example, but was mocked up rather quickly to show the range of motion for one of these setups. This drive setup is really cool because it allows for 8 directional movement, allowing movement in the 4 main directions along with the diagonals. If we name each wheel A, B, C, and D, we can go through and dissect how to make this system drive in all 8 directions. If we move wheels A and B toward the middle, and wheels C and D toward the outside, we move forward. If we extrapolate this to the other 3 main directions, we can see how to drive each set of wheels. Feel free to pause the video to see in more detail. If we want to move diagonally right forwards, we move wheels A and D in that direction. If we move them in reverse, we move diagonally left backwards. Moving wheels B and C forward, we move diagonally left forwards, and by reversing B and C, we move diagonally right backwards. And you can turn in a circle by moving all the wheels in the same direction. You might be saying, well, if it's so good, then why doesn't everyone do it? Well, from what I could find, the main downsides are less pushing power and less traction, which means that for some years, like in the zone, where pushing mobile goals was a major part of the game, this would be a pretty big disadvantage, but in shooting and stacking games, turning point, this drivetrain could be a huge point in your favor. Climbing over objects isn't the best, especially with the outer wheel guards, but if you could sacrifice those, I think that climbing might not be that big of a deal, especially if your drive is geared for torque. There's also a 3-wheeled holonomic drive, which is outlined in the excellent book Riobot's Combat Robot Tutorial, where it outlines 3 wheels set at 120 degrees from each other. However, this is difficult to make in Vex, seeing as there aren't gussets with that angle, and I wasn't sure how useful this knowledge would be in the Vex competition world. If you want this book, link.
Okay, so that's just like quick little kind of explanation of everything. And just to kind of expand on that, we're going to go over all the drives again. So the tank drive, typical 4-wheel drive. This one's this hybrid system where it has 2 Omni and 2 traction wheels. And as I explained, it's mainly just used to still have friction, so you don't have as much sideways pushing, but to reduce strain on the motors by being able to strafe side to side. Anything else you guys want to add, or just a quick little recap of those?
Well, I was talking about it a bit earlier, but a lot of tank drives will have 6-wheel setups so that they do still have the turning on the point while having the tractions in the middle. They'll be turning over the middle of their robot.
Yep. Okay. An example of this is a bigger picture of the robot we saw before. And this is a good example of a tank drive. So these guys have used some sprockets as well to increase the gear ratio. And yeah, as you can see, this is how a tank drive's built. Another example of a tank drive is Vex. And as you can see, they're using a 6-motor drive as well. Now, one thing you'll notice is both of these robots on the very side of the robot, they have this bracing. So their wheels aren't directly exposed to the outside. And as you can see, this one has a 5-bar on the side, whereas a robot like a Clawbot, as you can see, it doesn't have any protection on the wheels. I thought I'd just hand it over to Anthony and Jacob again, just to explain why that is a very important thing, especially at a more competitive level.
Well, basically, the main reason why you would normally want to have a C-channel just guarding the outside of the wheels is mainly because, for one, you need better stability on your wheels, because if you're just having one axle dangling out, you are placing a lot of pressure on the axle and the motors, and that could potentially damage your motor because it will be working a lot harder to get these flopping wheels just to rotate in one direction while it's trying to counteract that by being really unsupported.
Jacob?
Yeah, so that's what we call cantilever. And if you have a look at it, you have the axle is sticking through the wheel. And if you think about the forces, you're pushing the force up on the axle. And the further away you are from the point, the more torque you will have on the axle pushing upwards. It's a torque equals force times distance. And so a greater torque will mean you'll have a greater bending moment. The axle will want to bend further and faster, which will damage your axle and cause the wheel to not be sitting straight. Whereas if you support it on both sides, you're reducing the distance between it. You're giving it more support. It's less likely to bend. Additionally, if you're bending your axle on the outside, it will likely bend the axle on the other side a bit easier, and your gear might become disconnected from other gears it's linked to and skip a fair bit because of the bent axle.
Yeah. Okay. And then next up, we got Mechanism. Now, Mechanism, in my opinion, I I used to, back when I first started, when I was in like year 8 and year 9, I was like, oh, look at it, Mechanism Drive, that's so cool. You can do holonomic without an extra motor like a H drive, or we didn't have to build an X drive, you just use these wheels. But there are a lot of downsides to it. So maybe, did you guys just want to kind of explain why Mechanism isn't as good as you might think initially?
Primarily, the main reason why a lot of people try to avoid using these types of wheels is mainly because, if you can see from the demonstration, that these wheels consume a lot of space on your robot. If you use a conventional Omni wheel, it could take up 4 holes, and if you can see, just count the holes. Or if you want to take it to the extreme, it could take up 3 holes. And the advantage that gives you is that you can have more real estate within the center to add certain features that you want to use on your robot, or any little mechanisms inside your robot, or just more room for your battery and brain.
In terms of friction and all that, Jacob, was there anything you wanted to add?
They have higher friction, but another issue is this requires you either have to commit really to a 4-motor or an 8-motor drive, because you can't link the 2 wheels on the same side of the drive together, because they need to be able to just rotate opposite directions. Whereas with a tank drive, you'll often link your front and your back wheel together, so they're all being driven by the same motors. And what that means is, if one of the wheels for whatever reason is not touching the ground, the other wheel's getting the power from all the motors on that side to push it forward. Whereas if one of those wheels gets lifted off and you want to drive forward, you've just lost one of your drive motors from pushing. You've only got your back wheel pushing, not your front wheel, which will reduce your effectiveness there.
Yep. I couldn't find any really good examples of mechanism drives. This kind of proves that they're not used that competitively. But here's a robot that does have mechanism wheels. But as I said, I couldn't even get a really good picture because it's just not really used that often. X drives. So here's just a little CAD image of an X drive, and here is a top view. So X drives, typically what you'll notice is that they take a lot of space. And one of the things about Vex is you always have some sort of manipulator, which is an object that manipulates game elements. So you might have an intake or a shooter. Those are kind of considered manipulating mechanisms, right? With X drives, one thing that people often have is it takes up a lot of space to build it, which means there isn't somewhere you can attach these manipulators really easily and have a lot of open space within the chassis. Whereas if you might have a tank drive like this, you could kind of hollow out the middle and put everything else, and you could still have a tank, and it's kind of got this little like area in it that you can fit stuff in. There's not much internal room with something like this. Myself and Anthony built an X drive 2 years ago for Turning Point. Here's a little picture of the bottom of it. Now, we tried to get as much space as we could in the inside by kind of trying to minimize the amount of like bracing in the middle. But even then, we still struggled a lot with it. And we only used this X drive for one competition, which was the season opener that year. I personally really liked it. But the problem you have with X drives is that unless it is built perfectly, and unless it is like, you've made the friction perfect, it's always going to be a bit problematic, because one of our wheels, it had slightly more friction than the other wheels. So instead of it moving and strafing perfectly, it would always kind of be turning on a bit of an angle. So we could never, it was always a bit harder for the driver because they'd always have to adjust for this slight deviation. So there's small little things like that you have to keep in mind with X drives. There's a high skill cap, and there's also a lot of downsides to them as well.
Yeah.
Did you want to maybe go over the downsides, Jacob? Or?
Oh, okay. Well, back to the mechanisms. It's like the mechanisms in that you can't link your drive sides together. So every motor is independent, and if a wheel gets off the ground, again, you're not getting that power. This doesn't come off as very like, I've said this in the chat, but it's not very intuitive, but a X drive will have a faster drive speed than the same ratio on the same wheels in a tank drive formation. You have the way vectors add up, you end up getting 1.4 times the speed, or you got the drive times root 2, which also means you've got 1 over root 2 times the torque. You've got less torque. So people will think that their X drive's not as strong as their tank drive because they didn't realize that it is getting lower torque for being on the same ratio and going faster. And yeah, if you don't build it right, it doesn't work very well.
Okay.
That's the main things.
Yep. So now just quickly we'll go over H drive. So H drive is essentially the same as a tank drive. The only difference here is that you have a horizontal wheel in the middle, which is powered by a motor, so that that motor can drive and take advantage of the omni wheels. So you can still have that strafing movement and still be able to drive forward and backwards. I guess what's the main downside of that one? Again,
considering V5 is such a such a powerful asset, people don't like to use this type of drive as to waste one motor just for one function, like it's doing like there, right in the middle.
Yeah.
People
on Cortex, you had 12 motors, so
yeah,
it was more doable.
but for this, people are generally considering that this is just a not viable option, just mainly because these motors are such a viable asset. They would rather use this for anything else, such as a lift, an intake, or a a flywheel, or any other outputs like that, other than just one singular purpose like this.
Okay, here's a quick example of a H drive. This is the bottom of a H drive. As you can see, it's a 6-wheel drive with one in the middle, and that wheel, as you can see with the shaft, is powered by a motor, which does allow for
wow,
strafing.
That's a long shaft.
That is, I would personally not use that, but yeah.
That would twist very badly, I would feel.
Look at the connection points though.
Yeah.
Is that motor connected?
Yeah.
Doesn't look like it.
Then lastly, we'll just quickly go over the last drivetrain, which is a Kiwi Drive. So we'll watch this little video. It's a quick little short one. Kiwi drives are not used competitively. I don't know any Vex team that's actually built a Kiwi drive in VRC and used it and had success. But
it's an X drive, but worse.
Let's just watch it.
Oh.
It's literally a bit of a meme. Like, I couldn't even find a VRC video of a robot that has Kiwi Drive. It's really hard to like build, and the downsides far outweigh the advantages of it.
You only have 2 of the wheels powering at any time if you're driving in a straight line, really. It does mean you can use less motors on the drive, but often in competitive Vex, you need at least 4 motors on the drive to have enough torque to be able to do things like climb up the platform this season. Or if someone's pushing you, if you have a 2-motor drive, you can't handle pushing back.
Yep.
You need at least 4.
Just quickly for everyone, I have a feeling we're going to go a little bit over time. So just to let everyone know that if you guys do need to leave at exactly 8 for any reason, feel free to. But we're going to keep going until we finish, I guess. So next up is lift systems. So what we're going to do is we're going to go over lift systems now, and then we're going to go over some additional intakes. Then we're going to put everyone into breakout rooms for like 2 or 3 minutes. I know some people don't really like breakout rooms, but maybe kind of just talk about maybe what drivetrain, what lift system, like what one of each kind of thing we're going over you think is the best for this year's game. And then we'll all come back, and then we'll just have a quick little discussion about what we think about that. I have a feeling everyone's probably going to come up with the same kind of things, but it'd be interesting to see what everyone thinks. Okay, so lift systems. The famous double reverse 4-bar, or as Jacob refers to it, the reverse double 4-bar. There's a lot of arguments about whether it's a DR4B or an RD4B.
That's a single 4-bar, Spencer.
Oh, this is a single 4-bar. I'm sorry. We're gonna get to double reverse 4-bar.
Spencer cancelled. He doesn't know his stuff.
Fake
Vex
I got confused.
Fake Vex team.
All right, this is a single 4-bar. And they're very easy to build, and they're reliable, and they don't require that much maintenance. So the end of the lift, as you can kind of see in this picture, it's parallel. So maybe I'll let you guys explain it. You guys are builders. I'm not. Do you guys want to explain a 4-bar?
Well, so when you look at lifts, you include the tower that they're attached to as a bar. So if you look at the bottom left, you can see there are 4 bars involved. You've got, if you power one of those bars, the ones that are on an angle, it will rotate like a simple arm. And because of the way that it's linked with the right number of holes between them on both ends, the bar at the end will stay the same orientation, the whole rotation around. You can build it with different hole spacings in there to have a non-parallel 4-bar, but that's a bit more advanced than I think we'll cover here. The advantages is if you have something that must remain exactly straight as it goes up.
Yep.
Disadvantages is the lift moves forward as it goes up and then comes back. It moves in an arc. So everything will be getting away and getting closer. So it's not good for placing on a fine line in a specific spot as you get up to a different height.
Yeah, okay. And then, as I said before, DR4Bs and RD4Bs, that's the next thing. And that's where you combine 2 different 4-bars together. So this is a DR4B. So as you can see, it has one 4-bar in one direction and one in the other. So it's reverse, right? And includes 2 iterations of a 4-bar. It's a relatively linear lift compared to the single stage lifts. And if built properly, they can reach heights that a single stage wouldn't be able to. You can replace the second iteration of the 4-bar to a 6-bar if you want to increase the height a little bit. These are harder to build than a normal 4-bar, and they are a little bit more difficult to code. And they are prone to more issues as well, so when they're not built properly. So they are heavier, they require more space. But yeah, do you guys have anything to add, or?
The main advantages why people would want to use this is that what was it? The main side that you're trying to lift up will move in a linear pattern. It doesn't move in an arc as well. As in a perfect world, both the lower and upper arms will be moving at the exact same movement. So it will just require the top arms just to move in a straight line.
That's the whole moving in an arc. So the middle stage moves in an arc, and then the top stage moves in an arc, but that arc is cancelled out by the arc at the bottom.
Yeah.
As long as you've linked both stages together, like if you have a look there, they have the bottom stage rotates gears in the middle that then rotate the top arms.
And why I say it's in a perfect world, like sometimes it will move slightly in arc, but that's generally negated because the Vex is really just a very rough sport, and it's not going to be perfect 100% of the time. So you can get by on just a bit of error.
Yep. Okay. And then kind of double reverse 4-bars are broken down into different categories. So this is what we would consider a heavyweight. And these are powered from the bottom and the middle. They have a very heavy top manipulator, as you can see in BLRS's robot here. A lot of boxy channels, they're very tall. You can kind of tell by looking at it like that's a bit more built than maybe a smaller 4-bar, like a lightweight, which we'll show you now. These I would consider more all-around DR4Bs. They're a bit more reliable. They generally use 2 motors. They're quick, they're tall, they're easy to make, and they're powered in the middle. They have a lot of cross bracing, and they're pretty much structurally made up entirely of 2 wide C channels. So the robot on the left here is me and Anthony's robot from Tower Takeover, so a bit over a year ago. Ours, I wouldn't say was that conventional in terms of an all-round. It kind of fits in like this all-round middle kind of section. But ours, we only used 1 motor, so ours was just not powered as much, but it is still classed, I guess, as an all-round. And then 491A on the right is a bit of a better example of all-around. It uses 2 motors, 2 V4 motors, and yeah. Then we have this lightweight. So this is the pylons from Canada, 5225A. The DR4B, for instance, these are good options for motor efficiency and lighter game elements where you just have a lift because you need a lift for maybe like a smaller kind of scoring element, like maybe caps in turning point. You don't want to dedicate like a lot of elements to that. Sorry, a lot of motors to that. So that's kind of the instance where you'd want to use a lightweight, I guess. And then featherweights are even lighter, and they're just really, really, really simple, quick 4-bars. They just strip down the concept to the very basics. They're very space efficient, and they have another actuating device or lift on the end. I believe that kind of wraps it all up. I guess you guys would agree.
Yeah.
Just the difference. Yep. I'm just going to try speed through because I don't want to run too much over. And yeah, there's some main components to success when building these lifts. And these can be broken down, I think, into planning, designing, robustness, and efficiency. Planning is just more like, setting your constraints, knowing what you need to do. Designing, you could use CAD tools such as Autodesk, just to design to make sure everything's fitting in well, make sure it's robust.
As a Vex team member, you have free license to Autodesk as a student.
Yeah, so you guys can all get Autodesk for free. So that's really useful. And I'd start playing around with that as well. Make sure they're very robust, lots of bracing, and also that it's really efficient. Yeah, did you guys want to add anything, or that's just
that's basically the gist of it, really?
I think what was the other one you mentioned before, Anthony? Another component you thought?
Just for liability, really. Like you don't want a robot to say it works instead of it works reliably, because it could just work one time and then it doesn't work the next time. So you want to constantly test for any weak points in any design of your robot.
Yep. Okay. And then we've got other lifts. So this is a scissor lift. So if you can kind of imagine, I'm sure you guys have seen them before in the city, for instance, where you had these little lifts and then they kind of extend like that when the people are standing at the top, right? Those are great examples in the real world of scissor lifts. So Jacob, Anthony, do you guys want to maybe just quickly explain scissor lifts?
It's a linear lift, so you don't have to worry about it moving forward or backwards as it goes up. Usually when built out of Vex components, there's not a lot of stability in a lot of people's designs. So they work all right for short lifts, but if you're making a tall lift, you'll have too much give in your joints generally. So as you get to higher and higher stages, there's less stability. And additionally, it requires sliders at the bottom generally. And sliders are, as we've mentioned earlier, generally high friction unless you make custom ones.
I think and also depending on what applications you're using it for, the main downside of why people generally don't like to use these is that, as you can see from the demonstration, it consumes a lot of space on your robot just to get it operational. And if you want more stages, it will also consume more space on your robot, which is the general reason why people like to use double reverse 4-bars as opposed to this method.
And then just expanding on that, we have a little demonstration video here, which we'll quickly watch. We'll skip through it a little bit.
This next.
Try the original video I had got taken down, so I don't have access to it anymore.
Which video was that?
I just had a reveal, and it was a scissor lift, and I had it, and then just disappeared.
Why didn't you show McChicken?
Oh, I should have looked at McChicken. Yeah, so I guess let's wait. Let's hopefully. All right, I think it probably starts around here. So pretty much the linear slides move out. And you can kind of imagine it like scissors.
It gets closer at the bottom.
Yeah, this one's built a bit lopsided, so it's not going linear completely up. But generally they would stay very central. Okay, moving on now, we have kind of some other lifts. Now we don't have independent pages for every type. We kind of just chucked a couple together. So the image on the right is what we would consider a 6-bar lift. They're relatively easy to build and maintain. And if they are built properly, they can reach higher than 4 bars. They're very easy to implement, especially with the double reverse 4 bars. If you want to have a 4 bar, then a 6 bar, for instance. More torque is necessary to lift to the full height. And they are front heavy because they're not moving directly up. And they're more likely to tip forward. They require a bit more horizontal space. Yeah, did you guys want to expand on the 6 bar at all?
Oh,
Not
really?
really.
Pretty self-explanatory. The one on the left is myself and Anthony's robot from 2 years ago. This isn't a 6 bar. It's not really considered a 2 bar. It's more what we'd say is a simple arm. That's Jacob's definition of it.
As
so
you still
that's kind of
demonstrated
its
to
own thing. You can just have an arm that lifts up. Fairly simple and easy to
Just
implement.
bolt a C channel to a gear
Yep.
and you're off.
There
It
you go.
rotates.
And then here's kind of the other 3 lifts. The top left, we have a chain bar. They're very compact and lightweight. They have moderate buildability, with it being comparable to 2 bars. They maintain.
What was it? But you might want to like never consider it being too reliable, because these chains are again made out of plastic and they have a lot of give. So the output of the bar on the chain bar will just rotate in any fashion depending on what load you give to it.
The maintenance might be slightly harder as well, due to the chain tensioning. And there's also a chance the chain may break. So they're not used as often because there's that high risk that might happen. The image
benefit to a chain bar over a simple arm is that you will have the same orientation of the end through the whole rotation of the arm.
Yeah. On the very right, we have a 2 bar. So that is literally just 2 bars, including the tower, I guess. Don't really need to explain those ones much. They're pretty standard. They're very, very easy to build, but they don't reach as high of a height as something like a 4 bar or a double reverse. And then in the bottom left, we have a cascade. You kind of imagine like a forklift where it has a section that goes up, and then you might have another section that goes up. And then those are built mainly with chains. They have very, very linear movement. They're compact relative to other bar lifts, and the mounting point can be easily made as a flat surface. They are mechanically inefficient due to the surface contact, and they're relatively hard to build. And there's multiple stages.
Yeah. And also they're incredibly hard to maintain, and only a small handful of teams have actually ever bothered to invest their time into using this method, as the material consumption is really high. The skill ceiling to actually implement this into your robot is also pretty high, as well, as you need to design a lot of your robot around this core lift by itself.
Aura leaks, we're working on a cascade.
Oh, interesting.
Unless you are a Jacob and you just become a nutty person like him, but that's a whole different story.
Okay. So now we're just gonna go into some shooting mechanisms, and then maybe some other applications. I'm gonna go into those breakout rooms. Just quickly though, before we do that, I just want to ask again. We have a attendance form for everyone from the University of Melbourne. I know a couple of people have joined since the start. So I'm just going to post that again. So if you are from our club at Melbourne University, make sure you fill out that attendance form. It's really important that we mark our attendance. Yeah. Anyway, back to the presentation. So yeah, shooting mechanisms. There's a lot of different ones, and we're going to look at Jacob's reveal from a couple of years ago as well. So this here is what we call a puncher, and we were alluding to this a bit earlier with the linear slides as something that's very useful. So let's watch this little quick demonstration video. That was pretty much that. And here's a
yeah. Just as a statement, because people might not know how that was firing, the gear that's turning it is missing teeth. You might see, if you look closely there, a bunch of the teeth have been shaved off so that the teeth pull it back, and then it reaches where no teeth are pulling the gears, and it shoots forward because the rubber bands are pulling it forward.
Yeah.
And you'll notice later when you see my catapult, that's how my catapult fires as well. It might be a bit harder to see, so I thought I'd point it out here.
Yep. And also, as you can see in this image a bit clearer at the very top, you can see the gear shaven. And I'll just kind of add this one here has a limit switch at the end, so that in the program it can detect when it's gone a certain distance back so that it can shoot. They're very simple to build, and they are one of the most effective ball launching mechanisms. They're relatively compact, and it doesn't lose any energy to spin, like flywheels, for instance. It has a less violent firing action. Obviously, there's some safety issues. You don't want to stick your finger in it. Not a great idea. I wouldn't try that. But yeah, an example of a shooting mechanism that's very useful. Definitely would recommend using punches. Now onto catapults. We don't really have any images, but we're going to look at Jacob's video, and then maybe you can just break down a couple things in your robot for us. We'll just do like a little general thing. So do you want the audio, or do you want to kind of talk over it?
Yeah, mute it so I can talk.
Okay.
So first you'll notice my shaky hands when I try to record. Yeah, I can't hold a camera still. But what you've got here is we've got a little roller there that's to pick balls up. So the balls would go up the front of this robot with all these rubber band things rolling. So we can just drive into the ball and it's picked up. We had a motor dedicated to flipping over those objects. Kind of waiting till we get to see the catapult. So my catapult could shoot 2 balls at the same time and hit the targets from a range of different distances. So that was specifically called a Hayukapult that season because someone who came up with it was called Hayuk. So what we had is, there's our catapult and 2 balls sat on it. It allowed us to shoot them both at the same time, which we felt was the optimal way to play the game. There were people who used flywheels, but the speed of being able to hit 2 flags at the same time and just immediately have 2 more loaded in like that was quite alluring to us, along with how it's more hardware controlled rather than software controlled. With a puncher, you needed to have a mechanical change. And so there you see the catapult goes down, and that's from the same slip gear concept. Another feature of our robot is this ram here, which was passive. That didn't have a motor dedicated to it. We could just fire that out to ram people off that platform in the middle. What else is there to talk about for this robot? Yeah, I can't think of anything else that really needs.
Oh, there was that.
Yeah, so not many people could drive straight up onto the platform. We had designed our bot so that our rollers would be able to grip the platform and give us enough force to lift our front wheels up so they can grip the platform and then can pull us up on top of the platform, which a lot of teams couldn't do. Also designed, like you might have seen at the start, we had polycarb on the bottom of our chassis rails, which would slide better than the metal on the plastic of the platform, so that we would get that momentum to just drag us up without catching.
Yeah. Okay. Moving on a little bit. Now we have flywheels. So there's 2 different kind of flywheel designs we're going to go over: double flywheels and single. So this is a double flywheel. This is a very basic kind of example. This really reminds me, Anthony, of what we had in Nothing But Net. Like 5 years ago. We used a double flywheel. Regrettably, I don't think it was the smartest decision. Here's a very basic design. So pretty much you have these 2 wheels and you spin them both really, really fast, and then you run a ball through it, and then it kind of gets launched, right? The wheels are spinning, put the ball through, and it shoots it off. It's a general concept. So here's a better image of a double flywheel. This is VCAT's. This is a Vex Team's 15-inch robot, and this is their double flywheel. So they don't have a backboard like single flywheels, which we'll show you in a second. They do have 2 rotating wheels, and they're done vertically rather than horizontally. They're more advanced and they allow for more tuning. So, for instance, if you were to change the speed of one wheel in particular, you could technically shoot the ball on like an angle. So I don't know if any Vex teams do this in Turning Point, Jacob, but maybe from any position, both be able to shoot forward and to flags left and right. It's really hard to tune. It's
found it easier to just turn their robot.
Yeah, it is something that is possible. It's not necessarily something that's practical because the tuning is really hard, consistency, stuff like that. It is a possibility. There's a higher skill cap for double flywheels than single flywheels. And they have less backspin than single flywheels, I'm pretty sure. They are larger and they are heavier though. With that, we then have single flywheels. So here's two robots. We have 1104M on the left, and I think it's 169Y or 169A on the right. And these are both single flywheels. So as you can see, they both have like a hood on the back, which the ball rolls against. People use polycarbonate as it has less friction than the metal. And then that kind of rolls through and then shoots it forward. And then here's our double flywheel from afterwards. Sorry, our single flywheel from Afterworlds. Anthony, did you want to explain anything about our robot?
No, I as someone who likes to improve their robots, looking at this just hurts.
Yeah, this was arguably at the time our best robot, and then since it's not something we're as proud of now, but at the time it was very good.
Yeah.
It was very fond of the floor as well.
It was very fond of the floor. Yes, that's right.
Hey, wait. I would like to rebuttal. Spence, remember when you drove the robot off the table during the reveal?
Yeah, but at that point, our robot had this ability where it's just because a miracle of construction. We drove it off the table once, and it hooked on the edge of the table, so it was kind of like on a like it wouldn't fall. It would like go diagonal. So the joke was our robot couldn't fall off tables. Yet Anthony somehow managed to drive it off.
What can I say? I'm a man of many talents.
I remember Jacob. I think it was it you or Lachlan was like calling me. And he told me what happened, and I was just like, nah. And then I ran back and I see the.
I can't remember which one of us called you. We were just talking at the time and saw that.
arguably the best thing that happened that day.
It was very funny. It was, yeah. Anyway, kind of moving on. I believe Anthony, you sent me this video. This is a single flywheel. And I think you want to show off the turntable mechanism here.
What's up? This is Luke for Team 323Z, and
right, we'll mute this one. So what they did was they had their flywheel on a turntable so that they could kind of adjust the angle at which they were shooting without changing the robot's orientation. Is that correct, Anthony?
Yes.
Yeah.
They pretty much made a tank.
Yeah.
Essentially, yes. Especially if you look at the later reveals, you would see them quite literally cladding this robot in polycarbonate armor.
It's a very, very cool system. Yeah, so as you can see, it has this really, really intricate turntable system. We'll see. I'm assuming it fires, right?
Yep.
Yeah. One thing I'll mention about our flywheel that we showed in the last slide, it was also capable of double shot. Although unlike Jacob's where you can just shoot the two, ours was more based on programming rather than like a mechanical side. So it was based on timing and then changing the velocity of the wheel and then using like finding the velocity and then projectile calculations to figure that out. So there are workarounds if you can't build something in the software, although it's a bit harder to accomplish. Like you can't do that with a linear puncher, for instance. That's only capable of one. It's a bit more restricted. Yeah.
And you can see this is a good example of the original V4s, where if you can just count, there's 6 motors going straight to one component of this robot. And well, yeah.
Another thing about catapults versus punches versus flywheels, if you were using a flywheel, in most cases you had, well, 1 or 2 motors running. So with V5, you had 1 motor running the flywheel, and then you needed another motor to load the balls into the flywheel, which in some teams was individual motor or was run off of their rollers. But that meant that they were limited to, once the ball was ready to fire, they couldn't pick any more up. There was a ball limit of 2, but some of them needed their balls to be at the same, like they needed both of them to be at the right spot to fire both of them at the same time. So they had a motor dedicated to running what was called an indexer. There were workarounds, like one of the teams, 240p mentioned earlier, had their arm for flipping the caps, also could fire their what's it called? Their
Index or
flywheel.
string
It would
mixer.
load the balls in. It was called a string dexter, they called it. But with the catapult, we had one ball rolling our intake up into the catapult, and then the catapult was on one motor. So we were saving a motor over most teams without needing any extra thinking. With the linear puncher, they either had to load the ball into the puncher, fire it, load another one, and drive somewhere else to fire it, or a fair few teams at Worlds dedicated a motor to angling their puncher, or dedicated pneumatics to it.
Yeah. Okay, so now we're going to move on to the last section of the mechanical systems. We've already spoken a lot about parts and some applications of things. So now, yeah, we're going to run through a couple last things. We're going to do a quick little thing on these because we are running a bit over. We're still going to do breakout rooms just for a few minutes, just so you guys can come up with some stuff. And then we're going to come back, talk about those ideas, wrap everything up, and then we're going to run into a bit of a Q&A. And yeah, if we go over a little bit more, I do apologize. We just want to get all this content, make sure it's all, we've delivered everything that we want to. Okay, so the first thing up, as we've kind of seen in Jacob's video and a few other robots, there's these kind of rubber band driven intakes, right? And these are called roller intakes. Now, myself and Anthony, we use this, but we put an anti-slip mat over it. Pretty much it was the meta for every single robot almost in Turning Point, right? Do you guys want to explain why these are so good?
It was just that these rollers were able to conform to these objects very easily, allowing just for very quick and easy intaking. And also, since they could stretch, the rubber bands could stretch, it allowed for a large range of area. So you could just be very sloppy when you're driving and still collect the balls. But there were still a few other options out there that could allow for larger area for your driving, but these were the more preferred types compared to the others.
An alternative was using flaps, but a lot of teams would find flaps would knock the balls away. Along with it took a lot more flaps to have them be wide enough. So often teams didn't have enough flaps, but they had sprockets, spare, and enough rubber bands, because rubber bands are cheap like dirt.
And one other little kind of cheap alternative that me and Anthony, we tried it. We made a catapult after nationals as like a practice robot, and we used zip ties as an intake, which was a bit less conventional. I don't think it worked out as well as we hoped.
Like it
on
worked,
my national spot for Turning Point, we had rubber band rollers, but there was a point in the intake that the balls could get stuck if they didn't have enough velocity. So we added a zip tie in it that slapped the ball up.
Yeah.
And really excited the referees and commentators to hear tick, 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 every time our robot was on the field.
Oh, yes, my favorite. Okay, and then a slight adaptation of the roller intakes, the side rollers, which were more common in the zone when picking up cones. Jacob, did you want to explain these ones?
So, yeah, this is just two rollers linked together, running opposite directions. They just shove the object up into them. So a lot of people called those ones Goliaths. I really didn't like that name, but they could pick up cones quite quickly while relying on like a motor, rather than you had alternatives of people who would just clip onto it with what were passive or used a claw. This had more room for error than a claw because you could just touch it with the rubber bands and it would feed it up into it. Yeah.
And whereas like there was only one team that ever decided to go for passive and decided to make it work, but no,
that's not true. But there was one good team at Worlds, like in the top of the world.
Yeah.
Yeah. Okay. Then there's some other variations of side rollers, like what was used in Change Up. Do you guys want to go over this?
I don't have much experience in this. I wouldn't know too much.
Well, these rollers, they just run sideways, and you would drive into the ball. And this one has grip mat on it. A lot of them had flaps on them, and they would just feed the balls up, like just eat them up and from the front as they drove into them. it was better for their designs than having a roller on top, because the balls were just generally a whole lot larger. So having a top roller didn't feed them up as well, because they could only really fit one roller on, and they wanted to feed them into a specific sort of like chamber, so they'd have a row of them rather than like getting fed up in like the whole width. So these rollers allow a greater like error for grabbing than just a narrow grabber, but less error than there's less error than the roller from above. Sorry, I'm just blanking on what I was saying there.
That's right. Yeah. Just to move
they were just generally good at feeding in.
Okay. The next one was a bit more apparent in Tower Takeover. Anthony, did you want to go over this one?
These intakes were very well the predominant intake method in Tower Takeover, mainly as they were just incredibly simple to just build and very effective in this game for many teams. But what was it? The main issue you can see as all chains, they did have a tendency to break if you couldn't if you use them in the wrong situations, or just someone decided to smack into them hard enough. But generally people did have a roundabout way of preventing these by stacking a few more sprockets on the top and the bottom, just with lacing them with another chain just to act as pseudo intakes, but they weren't.
I put tensioners in between the C channel and the roll and the tread, so that there was just almost no point in which the force of the cubes was pushing against the chain. It was pushing against sprockets.
Mm.
Yeah. Okay. Next intake we have this, which was a bit more in seen in Starstruck, and it was kind of just this massive claw that would just grab as many things as it could at once, and then it would chuck them over. It's not as precise, but for that game, it was much more efficient and kind of because of the shape of the game elements. Whereas Tower Takeover with this intake, you had square cube elements. I've got one over there. Can't be bothered grabbing it. And then this one with balls. So it's kind of the intake's all based around the shape of the main game object. So just for this season, it was a bit easier. Did you use something different, Jacob?
We used a claw with a scoop under it. But what I was going to say is back to the last two. The reason why that one was fine for change up, but this one we didn't use those for change up. It's because the cubes needed to stay in the right orientation as they got fed up.
Yep.
So by having the longer tread, it meant that the cubes would go in straight rather than diagonally. Whereas with balls, you don't care about which orientation they go in.
And then, yeah, so that's pretty much just a claw. Last thing I'm going to go over is just wheelie bars. So wheelie bars, sometimes with the robot, it's unavoidable that it might be a bit too top heavy or the center of balance might be a bit off. So one thing some teams do is they just extend the robot out a little bit at the back and they add wheels so that it just kind of shifts the center of mass. And we call these anti-tips. Here's a little video of an anti-tip me and Anthony had on our robot during Tower Takeover. So at the start of the game, the robot had to be within 18 by 18 by 18 inches. But what we had was what we called a passive release mechanism. And how that worked is it doesn't require any motors. It just uses another system to work. So for us, whenever we had our tray, which would kind of open at the start of the match, that would release a little lock, which would then flip this out as soon as we started driving. So actually, it was attached to our wheels, I think, Anthony. Where as soon as it moved.
Oh
forward,
no, that was originally to our first design, but for.
And then at the end we changed it to the tray. Yeah.
Yes.
Yeah.
My one was powered. I had one that was powered by gravity. So when I drove forward, the force of moving forward, it would want to stay where it was, and so it would move backwards and then fall down from gravity.
Yeah. So there's a lot of different systems you can do, and then I think this is another video of ours just from the bottom. As you can see, we have this little bar here that it just moves out and then it flips it out. And then Jacob,
Oh, sorry.
No,
back to the video before. Sorry.
this first one, or
yeah, this one. Mainly, I always, every time I showed this to a lot of people who asked if they wanted to build this, I always encourage them to not build this, as this is an incredibly what was it, time-consuming way just to for a very simple problem.
Over-engineered.
Yes, incredibly,
Pretty much.
but it worked. You can't deny that. But that's why I always stray teams to go for the method like Jacob or anyone else's method, which was much more simpler.
Okay.
I don't know whether
Um,
I'd call my one simple.
All right. So
that one there was simple,
All right,
not the one on my.
let's look at this video. Okay, so this was also a passive release mechanism, and this was your tray deploy mechanism, I'm pretty sure.
Yeah.
Did you want to just explain kind of what's happening here?
So if you have a look, we had those side rollers for picking up the cubes. And at the start of the match, to fit into size, they were angled upwards. And then we needed this tray to also fit in size. So that was rubber banded up, but it was pulled down. And those two rollers held it in. And then by running the rollers outwards, as if spitting out the cube, it spits out the tray. And then the rubber bands flipped it back up into its final position. So it was no motor dedicated to flipping that out. It's all out, just rubber band powered. And from the actuation of those rollers. So we were reusing a part of our robot that already existed to do one thing.
And just to expand on that
Another
slightly, obviously you've got your tray here, and we would stack cubes on that tray, and the cubes are quite heavy. So especially at the top, it was causing the robots to fall backwards a lot. And that's why, as we mentioned before about wheelie bars, you can see Jacob here has a little wheel that's extended at the back, which is a wheelie bar, prevents it from tipping over backwards by.
And that one there was on a linear slider.
So that one was an active mechanism then.
No, it wasn't active. That was passive as well. I just don't have a video of it.
Okay. Now just before we go into the Q&A, can I just get, you guys can raise your hand emoji. Did anyone just raise your hand if you still want to do breakout rooms, or if you just want to maybe just say in chat what we think's better? Can you guys just raise your hands? Okay, so based on that, I'm guessing nobody wants to do breakout rooms. That's fine. It's probably better for the time that we don't. What we'll do instead is we'll just quickly go over together, just using the chat. Out of all of the different lifts that we showed you, based on this year's game, what lift would you guys use if you were building your own robot? If no one else, it was just you building a robot, what lift would you use? I just want to kind of see what you guys think. So just the options, double reverse 4 bars, 4 bars, 6 bars, scissor lifts, cascade. Did anyone have any ideas? DR4B? Yeah, what does everyone else think? I kind of want to see what everyone says. 4 bars. What else do we have? Okay. All right. Well, personally, I think I would use a double reverse 4 bar. Anthony, what would you use?
Personally, I would choose the double reverse 4 bar, but just for extra brownie points for excellence awards, I would go for the cascade lift.
Jacob, you mentioned before you guys are doing a cascade, didn't you?
Yeah, we have very tight space constraints, so
yeah,
cascade lift is very compact.
So,
and we can make custom parts, so it's a lot easier to make low friction ones.
Okay. Now, if you guys were building a drive, like just a normal chassis for driving around, what chassis would you guys go for? You've got tank drive, H drive, X drive, Kiwi Drive, or Mechanism. What's the first thing you'd go to for this game? Keep in mind, you've got to climb on the platforms, you've got to move around the field a lot. What do you guys think? Tank drive? What does everyone else think? Tank for space, 6-wheel tank. Any other ideas? Tank, yep. Need the tour for the seesaw. Kiwi for style. Okay, well, I think I would use a tank drive. Anthony, what would you use?
Again, better brownie points, right? Excellent award, we need this. So polynomic.
What would you use seriously though? What would you use if you wanted to win?
The drive that shall not be named.
No. Jacob, what would you use?
I'm using 6-wheel tanks.
6-wheel tanks?
Usually
Yeah.
I would just use a 4-wheel tank, but 6-wheel tanks what I'm doing this year with custom wheels for the middle.
I agree. I'd ask you guys about intakes. I don't really think anything we've covered today is super duper useful for this year's game in terms of the intakes and the shooting mechanisms. That's more for previous games or future games, so those aren't as relevant. But I generally think that we've gone over a lot of the main mechanisms we've seen really used over the last few years. Stuff like flywheels, punches, and catapults have been used over multiple seasons, like Nothing But Net and Turning Point. The double reverse full bars are seen like almost every season. So I feel like these are the more prominent things. Yeah, so we're just going to end the recording now and just say thanks, I guess, for watching. And then
I
we'll go
really
into our
recommend
Q&A.
watching reveals on YouTube. Other teams show off their robots.